So since we've seen how delta affects a solution for a given example, I want to talk more generally about the effect of delta on solutions. Because it's neat and it comes up in a lot of physical applications, and hopefully it helps you remember the rule for how to undo Laplace of a delta function. So remember that for the example we just did, the delta in the forcing term only happened at t equal 2 pi, but the solution to our differential equation y carried effects of that action for every time after that, for all t greater than or equal to 2 pi. So physically, I feel like this makes sense. This means that even if the forcing is temporary, we expect effects to persist. And I do want to mention with the caveat that we were thinking about an undamped spring, so somewhere where there's like no friction that would slow anything down. Then if you push this thing off the path it's on, it's going to experience the effect of that push forever. Whereas if there was damping, we know it's settling down eventually, so that push would also be damped and going down towards that equilibrium eventually. And then mathematically, this happens for like a really cool reason, which if you remember that t versus delta picture I drew for you, we're going to think about it for just this example where we did a forcing function at 2 pi. So our delta looks like this. Where for delta t minus 2 pi was our forcing term, and it happened at 2 pi and no other time. You can't tell that from the way I drew it because I'm bad at drawing, but we're just going to live with the imagination that it looks nice enough to convince you of that. And then the thing that we see in the solution, I'm going to give myself a little bit more space for that middle part, keep it kind of centered. So the thing that we see in our solution is against t, and we actually see this u term pop out, where after 2 pi, u would be 0, and then up here it becomes 1. Or like our u times sine is 0, and then it takes on that sine function. But I'm just going to show you u because the reason it has this nothing, then something behavior is because of the u part. And the way we move between these two pictures is that we need to remember that the integral of delta is 1, and that solving ODEs is just fancy integration. We're trying to get rid of derivatives. We usually integrate them in some way. We want to turn dy dx into y again. And so this u is representing the integral of delta. It's saying this integral, as I add up all the delta contributions, is 0, 0, 0, 0, 0, and then delta's infinity, which gives us the integral 1, and then new contributions don't do anything. It's back down to 0, 0, 0. So u, the result of integrating delta, starts down at 0, then at 2 pi jumps up to 4 sine, or it's adding this 1 times 4 sine, and then carries on forever at that same value. The long story short of this, that you all might care about, is that anytime you have delta in your ODE, you will have u in the solution. If you take Laplace of a delta function and do not introduce your Heaviside function at some point, it means something went wrong. So just watch out for that. And that's the last that we're going to talk about delta in these videos. So in the next one, we'll go ahead and move on to talking about periodic functions.